join. We are going to start with 8.3 today. And again, let me know if you have any questions or if you need to discuss anything about the homework. All right, so today we're going to solve equations involving a single trig function, solve trig equations using a calculator, which I feel like we've been doing that. Solve trig equations in quadratic form, solve trig equations using fundamental identities, and solve trig equations using graphing utility. All right. So the first example here is saying, if we're given a theta, how can we tell if it's a solution or not? If you think back to algebra, if you were given a value, how did you know when it was a solution?
We substitute it to the equation.
What was that?
We substitute it to the equation.
Yeah, and when you substitute it, what happens? What should you get out?
They should equal the same number.
So that would be a true statement. But so, okay, yes, you will get it to equal the same number, but it will be a very specific number. So if it's a solution, which would mean it would lie on the x-axis, what do you think it should equal? So I guess it should be equal whichever number they give us, but in this example, that solution should be a 0, right?
I think so.
Okay, I think I agree. All right, so if we want to determine whether theta equals pi over 6 is a solution for the equation 2 sine theta minus the root of 3 equals 0, what do we have to do? We're going to plug pi over 6 into the sine, right? So what's sine of pi over 6?
1/2, I think.
If you think, let's see. Yes. Okay, so 2 times 1/2 will give us a 1, 1 minus root of 3. Does 1 minus root of 3 equal 0? No. So therefore, pi over 6 is not a solution. Okay. What about pi over 3? What would sine of pi over 3 be? It's okay. Luckily, it's one of the examples, so they give it to us. Okay. If we plug it in, sine of pi over 3 is the square root of 3 over 2. The 2's cancel. Radical 3 minus radical 3 is going to give us a 0. Therefore, pi over 3 is a solution. Okay? Any questions on that? What do you have to notice? And it's written here for you. You can put it in your own words. You don't have to write that verbatim. What do you know about trig functions? Is there only one solution? No. Why?
Well, because it repeats each time.
Right, it repeats. So with every period, you're going to have so many solutions. So pi over 3, what would the next one be? Like 5 pi over 6 maybe? So you can't just stop at pi over 3. Notice it says pi over 3 is a solution for the given equation, not the solution. Okay? I think in Pearson, there's going to be a part where you have to answer like the next 5 solutions, okay? So this is saying unless the domain of the variable is restricted, so, you know, when we were doing the examples on Monday and it said it had to be between negative pi over 2 and pi over 2. So if you have a restriction, then you can just have one solution. But if you have the whole period or the whole equation set, then you're going to have infinitely many solutions. All right, so let's look at the next one. If you want to solve the equation cosine of theta equals the square root of 2 over 2, give a general formula for all solutions. Okay, list 8 of the solutions. So when does cosine equal radical 2 over 2?
Pi over 4.
Okay. So pi over 4 and 7 pi over 4. So those are just 2 of the angles, but it wants to know the next 8 solutions. So how many more do we have to go? A bunch, 6. Okay. How would you do it? What do you think your next step should be?
You should add 3/4 to 7 pi over 4. I mean,
3/4? What do
no.
we know? What do we know about the period? The period is 2 pi, right?
Yes.
Okay. So to find the next set, you just want to go one more rotation, right? That would be the next set. So here it shows you a really nice formula. You probably want to write it down. If theta equals pi over 4 plus 2k pi, or if theta equals 7 pi over 4 plus 2k pi for k being any integer. However, did it say just the first 8 or did it say any 8? It just says any. Okay, so if you needed the first set, they would probably tell you where your starting and stopping point was. So, all right, so here it gives you the nice little formula. You probably definitely want to write it down. I can circle it for you if I get the right tool open. It's not opening. There it is. Okay, so if we wanted to highlight, that's important, I would write it down. Okay. And then if you didn't believe the slide, if you said, no, that can't be right, you can plug it in. If, you know, you put in cosine of negative 7 pi over 4, well, you should know it should work. All right, any questions on that? No? Okay. All right, so this is talking about finding the solutions to an equation. The first thing you have to do is solve it. How many of you could have gotten to this step without seeing it? It's just basically algebra, right? Except instead of having an x, you have a sine theta. All right. Now, it's giving you a restricted range, a restriction here for your period of 0 to 2 pi. So do you think that has an impact on what your answer would be? Okay. I will tell you that sometimes Pearson does some things that's really annoying. I'm not sure how many of you had issues on, I think it was 8.2, number 15. For me, it was 15. I put in the right solution and it told me it was wrong. So I just had to rewrite it in a different way. So it was completely equivalent and then it accepted it. So just be careful. If you end up finding equivalent solutions and Pearson doesn't give it to you, email me and I will go in and verify that it is an equivalent solution. All right. So between 0 and 2 pi, we're just looking at 5 pi over 4 and 7 pi over 4. All right. You do not need to have 8 solutions. You don't need to have 6 solutions because we have a restricted interval. All right. Any questions with that? No? Okay. Honestly, though, guys, if you don't ask the questions, I can't read minds, so I'm going to assume you're all good. All right, example 4, we're going to talk about finding the solutions of trig equations. So if we have sine of 2 theta equals radical 3 over 2, and our restriction is between 0 and 2 pi. So radical 3 over 2 happens at pi over 3 and 2 pi over 3. You can literally draw the figure out if you need to. Right there. Okay. All right. So we're trying to find all the solutions. So 2 theta has to equal pi over 3 and 2 pi over 3. The period of y equals sine 2 theta is just pi. So the interval cannot include 2 pi. So then it intersects 4 times. Here you can see it again. All right. I would not expect any of you to actually be able to draw that. What's the word I want? Not, obviously you can draw it the way they did, but that's probably not the scale. I don't think a lot of people could just eyeball radical 3 over 2. All right. And so what do we do once we find the 4 solution spots? So to find the solutions, we're going to use the general formula, which we already talked about that formula. But then instead of equaling it to theta, they had to equal it to 2 theta because of the equation. So then they had to manipulate their variables. Make sense? Okay. Once they put everything in, they found it right here. All right. So over here, we can see the K values that they used. Why do you think they had to use 0, 1, and 2?
because aren't they the points inside the restricted range?
Right, so they were looking for those next three, okay? All right. All right, so this one says solve the equation tangent theta minus pi over 3 equals radical 3 between 0 and 2 pi. I'm gonna give you guys a few minutes to think about it. So what do you guys want to consider with that? Where are you looking? All right. When someone has it done, if you want a chance explaining it, let me know. Because you can explain it, or you can let us know what your answer is, and we can see if it matches. Okay. All right, so here it's saying that the period of tangent, it's reminding you, is pi. So then the interval is from 0 up to pi. The tangent function has a value of radical 3 when the argument is pi over 3. Because the argument is theta minus pi over 3 in the given equation, write the general form that gives all the solutions. So you can see right here that they had to rewrite the general form. Okay? How many people got to that point? You got one. Do I got another one? Good. Okay. All right. So if we plug in our k values, then the solution that we find are 2 pi over 3 and 5 pi over 3. Okay? Because that's what falls in the interval. Any questions on that? Okay. All right. So this says use a calculator to solve the equation tangent theta equals -2. Express any solutions in radians rounded to 2 decimal places. I will tell you, you have to watch what they want on Pearson. You could be going through super duper fast, degrees, 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 and then all of a sudden they're throwing a radians at you. And you're getting really mad and frustrated as to why you're getting the problem wrong. Pay attention to radians versus degrees. It will give you incorrect answers you start to think that you just paid a whole bunch of money for a calculator that doesn't work, just pay attention. All right. So this is kind of nice because it does break it down for you to show you how you would put it in the calculator. Obviously, most importantly, let me find some big obnoxious coloring. Here you go. First set mode to radians. All right. Then you want to use the tangent inverse key. All right. Once you plug that in, you'll get negative 1.107, which rounds up to negative 1.11. That's in radians. Okay. Because the definition of y equals tangent inverse of x, the angle theta is obtained between negative pi over 2 and pi over 2. Then you have to include the 2 pi minus 1.11. All right. Okay. So once you do that, you'll get two solution sets, and here they are. All right. I highly suggest if you are taking notes in a notebook that you also consider writing out the diagram. I don't know how many times I will express that I think diagrams are very, very helpful. There's definitely been some problems that I've done on here, on Pearson, and the only way I was able to get it correct was once I did the diagram. Okay. Any questions on that? No? I can tell you guys, just as a side note, we moved this weekend, and I thankfully know where all my electronic stuff is, but our lives have been so chaotic that I am using my emulator on my cell phone, which drains my battery like crazy because I haven't been able to charge my new calculator. It's very sad. All right. Example 7, solving a trig equation quadratic in form. Okay, so we're looking at 4 sine squared theta minus 1 equals 0, and we're going on the interval of 0 to 2 pi. Okay, we treat this as if it is a regular quadratic. Sine theta is no different than x squared, y squared, z squared, whatever you want to make it squared, as long as you realize that in the end, you have to go through and figure out what theta is, okay? So here we go. Their solutions are pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. Does anyone have any questions as to how they got to it? All right. I'm assuming if you have no questions, then we are solid to keep going. All right. This one says solve the equation 3 cosine squared theta equals sine squared theta. What do you think you have to do? We have some room to write if someone wants to tell me what they think we should write down. All right. Let's check it out. How many of you assumed that we would use the Pythagorean identity when you saw that problem? Okay? It definitely should have jumped out at you because you have cosine squared and you have sine squared. Okay? Now, can you just simply plug it in? Are you allowed to just throw in maybe 1/2 here and 1/2 here and you're good to go and you're done? No. Yeah, okay. You have to make some changes, right? All right. So they used the definition of Pythagorean theorem to rewrite the equation so everything is written in terms of cosine. All right. I'm sure you could have done it the other way. In fact, if someone has, let me know and you can write it out. Bet you end up with the same answer. So 4 cosine squared theta minus 1 equals 0. Then they go through and factor. Okay. So you get negative 1/2 or 1/2. Anybody need that for a few seconds longer if you're writing down notes? All right. So solving each equation in the interval 0 to 2 pi gives us pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. All right. So again, guys, the interval here is very important. What do you think their technique is going to be for example 9? What do you guys think? Okay. So if you take a look, we're probably going to use the Pythagorean identity because we have sine squared. Okay. So sine squared's right here. And then, oh, look, we have Pythagorean identity. Okay. All right. We also have to consider cosine. All right. So again, they chose to rewrite for cosine. So 1 minus cosine squared theta plus cosine theta equals 3. They've rearranged. And then what? What does this look like?
How do they apply the Pythagorean theorem to the equation?
So they've replaced sine squared theta with 1 minus cosine squared theta.
Okay.
And then they simplified. So right here, they kind of show you this
Also,
as
okay,
why they did it. Like these are separate. These are not
so,
the same.
so they solve for, in the Pythagorean theorem, they solve for sine squared and then they substituted whatever sine squared to the original equation?
Correct.
Okay.
That's a whole separate step right there. I don't know why they put it there. It really should have been moved up. Okay, so once they did that, they then rearranged their equation. And what does that remind you of right now? Cosine squared theta minus cosine theta plus 2 equals 0. What should that be reminding you of?
Quadratics.
So we're going to treat it the same way. All right, so if you recall, we used to use the discriminant to find out something about our solution set. So we have a 1, a -1, and a 2. So that gives us 1 minus 8 equals -7. -7 is less than 0. So there are no real solutions. Okay. Any questions on this? Definitely might want to write down this technique. Maybe something that you might come back to, might end up using it. Okay. All right. The last one is talking about a graphing utility. I'm assuming this could be your calculator as long as it's a graphing calculator and advanced enough. I would probably just use Desmos because I just think Desmos is nicer for trig functions. It gives you a really great big screen. All right, so 5 sine x plus x equals 3. Express the solutions rounded to 2 decimal places. Okay, so each solution is the x coordinate of the intersection between, y1, which is 5 sine x plus x, and y2, which is 3. All right, there are 3 points of intersection, and here you go. All right. If you didn't believe the slide, what could we go do? If you didn't believe the slide, what could we go do? We could go plug both of these equations into what? Into either the graphing calculator or the Desmos, and we could verify it, okay? All right, last one for this slide. It's just showing, so it literally showed you it, okay? The thing that's super nice with Desmos that I like a little bit better than with the regular calculator is with Desmos, you can click on these intersection points and it gives you a nice little dot and tells you what it is. Whereas on your regular graphing calculator, you still kind of get that, but you have to either go in to the table or you have to go in and say value and then select the value and then it tells you what it is. I definitely prefer Desmos over this. All right, we still have some time, so we can go on to 8.4. And you guys are always more than welcome to work ahead if you end up having time and you see that you're understanding the concepts. You can definitely work ahead. I have no problems with people working ahead. Just as long as you don't miss due dates that you currently have. Can you see this screen loading or do I have to do a new screen share?
I see it loading.
Okay. All right, cool. I was worried I'd have to do a new one. I would love if it would actually load though. There we go. I just had to refresh the page. Solid. All right, trig identities. I think I've showed you guys this before. I use this handy dandy, what I think the internet called a trig cheat sheet. Literally, I think that's what you Google, trig cheat sheet. That's what I use. It has all the formulas and identities on it. And then on the back, it has some of the laws and the inverses and the unit circle. If you don't have one of these already, I highly suggest you get one. They're free. Just hit print, or you can handwrite it out. I guess if you hand wrote it out, you would definitely, you'd definitely know them. And I guess if you really have a hard time and you can't find one, you can always email me and I will share my resource with you. But really, it's just Google. I think you guys can handle it. All right. So objectives, we're going to use algebra to simplify trig expressions and establish some identities. So I think this might literally end up being like a proofs lesson. All right. So here's a definition, which means if it's saying definition, you might want to write it down. Two functions f and g are identically equal if, obviously, f of x equals g of x. For every value of x for which both equations are defined, such an equation is referred to as an identity. An equation that is not an identity is called a conditional equation. Okay? Considering how I get my exams for this class because of the way I've chosen to do it, I would not be surprised if these are either on Pearson for your homework or if they're going to be part of your exam or quiz. I would definitely write them down. All right. Any questions with that? I think that slide's pretty self-explanatory. Write these down like crazy. If you're watching the recording, push pause. Obviously, you guys can't push pause because we are live right now. But go ahead and write these down. Quotient identities. Tangent theta equals sine theta over cosine theta. Cotangent equals cosine over sine. That might seem redundant because we've been talking about it practically since day one, but they do actually have names. So those two are your quotient identities. You also have three reciprocal identities: cosecant, secant, and cotangent. You have three Pythagorean identities. And then you have 6 even and odd identities. That is not where identities stop. That is only where identities kind of start. So I guess in terms of identities, that's about it. But there are many formulas. A vast number of formulas. I don't know if we're going to get to all of them or not. Okay, so we'll do some highlighting. Quotients. Okay. Reciprocal. Pythagorean. And even and odds. Do any of these look brand new to you? Okay. Some of them should definitely be like, oh yeah, we've been dealing with that kind of the whole time. Some of the ones that might look a little new to you right here. This one might be a little new to you. This one might be new to you. All right, these we've kind of talked about, but maybe did not really, make the general statements that are being made now. All right. Going to see what happens if I save this. Oh, that's rotten. Oh no, The whole thing shows up. So that's cool. All right, neat. So if you missed this, it will also be up on Canvas. I can add it to Canvas. How many people need a little bit more time to write down the identities? Okay. Again, if you would prefer them to be typed or along with some resource, they are out there. Okay. Just to review, and I know most of you were pretty good with your algebra quiz, so I'm not too worried. 4 basic algebraic techniques that we're going to use for establishing identities. Rewriting a trig equation or expression in terms of sine and cosine only. So that's something you might want to take note of. You want to try to rewrite them in terms of sine and cosine only. Okay. If you can get it rewritten into sine and cosine, then you're probably at a good start. Multiplying the numerator and denominator of a ratio by a well-chosen 1. Writing sum of trig ratios as a single ratio. And factoring. Okay. Anyone have any major concerns on those techniques? Okay. Not 1,000% sure what they're talking about with the multiplying with a well-chosen 1, but my assumption would be that if you needed to get rid of something, obviously multiplying by 8/8 is not going to change your equivalency. I'm assuming that's what they're going with when they say that. All right. Oh, good. They're giving us some examples here. So if we had to simplify the tangent of theta over secant of theta by rewriting each trig function in terms of sine and cosine, how would you do that? What would you write down? Well, we can do it off to the side. So tangent is what?
Sine over cosine of theta.
Okay, so sine. And if you guys are okay with it, I'm not going to write thetas out over cosine. And then what's secant?
Isn't secant just 1 over cosine?
Okay. So then now what should you realize? What's going to happen?
Cosine will cancel out.
Right, the cosines cancel out, so you're just left with the solution of what?
Just sine then.
Yep, just sine theta. All right. If we look at the next one, by showing that sine theta over 1 minus cosine theta equals 1 plus cosine theta over sine theta, by multiplying the numerator and denominator by 1 plus cosine theta. All right, so keep that in mind because that's going to be one of the ones that we're going to see on the next slide. And then simplifying with factoring, okay? You can see right away that if you pull a tangent out here, and then I imagine they'll do some other fancy stuff. So let's take a look. All right, so did we do exactly what they did for A? Yes, great. I just didn't separate it. That's the only thing. All right, let's look at B. So we have sine theta over 1 minus cosine theta times, so they're basically taking the conjugate. They did not really say that up. Okay. So what they wanted you to do here is they wanted you to start here And then I told you guys before, we were probably going to be looking at some proofs, and they wanted you to prove that you could get to here, okay? So that's what they're kind of doing with this slide here. So here they're multiplying basically by the conjugate, or you can see how 1 plus cosine theta over 1 plus cosine theta, that's just multiplying it by a 1, right? You could really cancel those out, but you actually need them, so don't cancel them out. All right? And then you continue working down, and you end up with where you were supposed to be in the end. Right? There you go. Okay? And then for number C, they factored on top, they factored out a GCF on the bottom, they crossed out, and they got to where they wanted to go. All right? Any questions with A, B, and C? Can you follow what they were doing? Okay? You'll have to do it yourselves, so hopefully that's a yes. All right. Example 2, establishing an identity. To establish an identity, they're giving us an example here of cosine theta times tangent theta equals secant theta. So they rewrote in terms of cosine and sine, and then at the very end, they realized that 1 over cosine theta equals secant theta. So they have proved what they needed to prove. All right, makes sense? So this homework is probably going to be a lot of proof. Like you're going to be doing some proofs. How you're going to be doing it in Pearson, it's kind of interesting. I'm curious to find out how they're going to do it. They probably will have you do like the multi-step answers, you know, the ones where you're like, why are we answering it like this? All right, so if we look at the left-hand side, because you're looking at negative thetas, we have to apply an even and odd identity, okay? So you find the even and odd identity that makes sense here, and then you just plug it in and work with it, all right? Again, that's another proof. Here we'll probably have another one. So they want us to establish why sine squared negative theta minus cosine squared negative theta over sine negative theta minus cosine negative theta would give us just cosine theta minus sine theta, okay? If you look at the left, do you agree that that is a more complicated expression? Does this look a little bit more complicated than this? Right? Yes. Okay. You also need to realize that the left side has negative thetas. All right. And then what you should realize over here is that we actually now have positive thetas. So something's going on there. Right? And it actually tells you down here. So we're going to start with the left side and apply an even odd identity. Right? Makes sense. Probably what you all would have started with anyway. All right? If you're writing notes down, this might be one you may want to take a note of because it probably will end up being something like it on the homework. Okay? So you figure out your identity here. You plug it in. You simplify. All right? And then you expand. And then you cross out. All right? I'll give you a few seconds to write it out. Definitely let me know if you have any questions. Okay. All right. And these PowerPoints are on Canvas. So if you need access to them, they're there. Okay. So example 5, establishing an identity. So they want us to go through and figure out why 1 plus sine theta over 1 plus cosecant theta equals sine theta. Well, look at the technique they used. Right away, they changed everything into sine theta, right? So then honestly, at that point, it's just a matter of rearranging and canceling out, okay? So they rearranged into sine theta, and then they combined their bottom fraction. And once they did that, they were able to eliminate, and then you can see where they got just sine theta out. Any questions with that one? Man, it must be a Wednesday thing. Algebra was almost just as quiet as you guys. I think you guys hit Wednesday and you're tapped out. You're like, I'm done. Just get me to the weekend. Just so you know, I do a lot of math on the weekend too. Do you know what times I like? I look forward to the in-between when there's no math that I have to do. I can just play video games. It's a really great couple of weeks. Makes me really happy. And then I get really bored, so I end up doing more work. All right. So we're going to look at establishing another identity. Here we have sine over 1 plus cosine, and then 1 plus cosine over sine, and that's supposed to give us 2 cosecant of theta. Well, someone explain it to me, left to right, what's going on? What do you think they used? So the first thing they did was what? They went from 2 fractions to
One fraction.
1 fraction.
And
Okay.
find the common factor between both fractions to combine into one fraction.
Mm-hmm. And just like you would in algebra, they realized, oh, it's kind of a lot easier if we just multiply these bottoms together, right? Okay, but then to do that, you have to figure out what was missing. So in the first fraction, you were missing a sine theta, which is why in the last fraction, you have a sine squared theta. Okay. For the other one, you were missing a 1 plus cosine theta, which is why you have 1 plus cosine theta quantity squared. Okay. So now they're regrouping. They're using the Pythagorean identity. They've canceled out after they've factored. All right, then you divide. Of course, 1 over sine theta is cosecant theta, so 2 cosecant theta. Okay. If I were going to have a question, it would probably be on this one. But we did break it down on the first slide. Okay. Establishing an identity. Here they're not using thetas. I mean, you really could. It wouldn't really matter. I'm not really sure why they're using this fancy, I guess it's a fancy U. All right. What did they do in their first step?
They use like the quotient identities for tangent and cotangent.
Yeah, they wrote everything in terms of sine and cosines, okay? It basically tells you step by step what to do. So change the sine and cosines, and then the next thing they're doing is adding quotients in the numerator, and then they divide their quotients, okay? Look at the nice little hint they're giving you there. Okay, they're giving you the Pythagorean theorem again. All right. And if I'm going too fast for you, just wait for the video and you can pause it and look at it. You can also pull it up on Canvas. Right. Establishing an identity. 1 minus sine theta over cosine theta equals cosine theta over 1 plus sine theta. Okay. So they chose to start on the right, and they're multiplying by that factor of 1 again. All right. And they're doing that. Why? Because now they can use the Pythagorean identity, and that leads you to cosine squared theta. All right. The cosines cancel, and here we have our end result. Right? Okay. Pretty easy section, I think. I would definitely write this down. Guidelines for establishing identities. It is almost always preferable to start with the side containing the more complicated expression. Why do you think that makes sense? If you have more things to work with, it's just like in factoring. Why would you start with the side that's been completely factored if you're trying to prove a statement, right? You're not always going to shove things in and it's going to be the correct guess. But if you're taking things away, you know what to take away, okay? Rewrite sums or differences of quotients as a single quotient. Sometimes it will help you to rewrite one side in terms of sine and cosine functions only. Honestly, you could rewrite both sides, but then just remember that in the final answer, you have to be where they wanted you to be, okay? You can't go to that sine and cosine option unless sine and cosine is what they gave you. Always keep the goal in mind. As you manipulate one side of the expression, keep in mind the form of the expression on the other side, okay? In a way, I would say that that this is pretty nice because you are you're kind of being told what your goal is or what your answer is, okay? But again, that just means that I don't know really how those homework questions are going to be, because if you're literally just being given